In this video, we're going to be talking about infinite series in calculus. So let's start off with this first question, and we're going to talk about if this series converges or diverges. So we have the summation of n is equal to 2 starting off. We have 1 over n ln n squared. So this is a classic integral test problem. What we're going to do is let f of x equal to that function, right? This function right here. And you're going to say for x is greater than or equal to 2, this function is positive, it's continuous, and it's going to be continuous, and it's decreasing. So now we're going to evaluate the limit. So we have the limit of infinity is a bound 2. We have 1 over x, we have ln of x squared times dx. So now we're going to use u sub. We're going to set u equal to ln of x, and du is going to be 1 over x times dx. So we're going to have the integral from infinity, 2. We have 1 over x, ln of x times d of x is equal to the integral of ln of ln 2 here, infinity, 1 over u squared du. So what we can do is we can rewrite this as a negative fraction, right? So we have infinity ln 2, we have u negative 2 du. So now we just are going to evaluate it basically. We have negative u to negative 1, infinity, ln 2. So this is equal to limit of b approaches infinity. We have negative 1 over u, and we have b ln 2. So this is going to be limit of b approaches infinity. We have a negative 1 over b, we're going to evaluate now, plus 1 over ln 2. So this is going to give us 1 over ln 2. So this is going to be saying that our improper integral converges. So therefore, by the interval test, this entire integral, the series, n is equal to 2, 1 over n, ln n squared, this is all going to converges. So let's do another problem. Let's say we have this integral, we have this series right here. N is equal to 1, negative 1, n plus 1, root of n all over n plus 3. So we want to figure out if this series converges absolutely, converges conditionally. Okay, conditionally converges, diverges, or if it converges absolutely. So let's check if it converges absolutely first. Well, we're going to consider the summation of this n is equal to 1. We have negative 1, n plus 1, root of n all over n plus 3. That's equal to summation infinity, n is equal to 1. We have root of n up here. We have n plus 3. So if we have a large n here, we have the root of n over n plus 3. That's approximately the root of n over n. So that's equal to 1 over the root of n. So now let's compare this to summation of n to 1. So this infinite series where we have 1 over the root of n as our function. This is going to be a p series with p is equal to 1/2. So because p is less than 1, it's going to diverge. So now we're going to use the limit comparison test. So we have the limit as n approaches infinity for n over n plus 3, all divided by 1 over the root of n. This is equal to limit of n approaches infinity, root of n, all over n plus 3, times the root of n. So we can cancel out that root of n, or no, actually, we can just cancel out that square root, We have limit of n approaches infinity, and we have n over n plus 3. So that's all equal to 1. So because this limit is going to be positive, and it's also finite, Therefore, our absolute value series diverges. Therefore, the original series is not absolutely convergent. So now we're going to check alternating convergence. So our original series was the series starting for going to infinity. We have n is equal to 1, -1, n plus 1, a to the power a sub n. Okay, so a sub n is equal to the root n plus 3. And what we need is for a sub n is greater than 0. So we have a limit of n approaches infinity, a sub n is equal to 0. So we have limit of n approaches infinity for the root of n all over n plus 3. That's equal to the limit of n approaches infinity for 1 over the root of n plus 3 over the root of n. So this is all equal to 0. So what we need is a of n to be decreasing eventually. So what we can notice is that a of n, when you have a large n, it's going to be approximately 1 over the root of n. And this is going to decrease. So like more formally, we can say that f of x is equal to the root of x over x plus 3. So if we differentiate this, we have f of x is equal to x power of 1/2 x plus 3 to the power of -1. So first we have x 1/2 x to the -1/2 x plus 3 to the power of -1 minus x to the power of 1/2 x plus 3 to the power of -2. So if we factor this, first derivative is equal to 1 over the root of x times x plus 3 squared times x plus 3 all divided by 2 minus x. And we can factor again. We have 1 over root of x plus 3 squared. And this is going to be 3 minus x all over 2. So we have that the first derivative is going to be negative when you have x is greater than 3. Therefore, we know that a of n is going to eventually be decreasing. So, therefore, we can say that by the alternating series test, the original series converges. So since it converges, but not absolutely, the series converges conditionally. For our next example, let's do this series. We want to determine whether this series converges or diverges. So let's say we have the summation n is equal to 1 series 3 to the power of n plus n to the power of 4. We have 5 to the power of n minus 2n. So our dominant terms are going to be exponential. We can see up here, this is going to be approximately 3n. Down here, this is approximately 5n. So we take the ratio of that. That is going to be 3 over 5 power of n. So we can compare this with this geometric series, which is summation infinity n is equal to 1, 3 over 5 to the power of n. So this is going to converge. This converges because we have 3 over 5 is less than 1. So if we use the limit comparison test, we have that the limit of n approaching infinity for 3 to the power of n plus n to the power of 4 divided by 5 to the power of n minus 2 times n, 2 times n, all divided by 3 over 5 to the power of n. We can rewrite this monstrous fraction as 3 to the power of n plus n to the power of 4 all over 5 to the power of n minus 2n times 5 to the power of n all over 3n. So this is equal to limit Okay, forgot to write the limit over here. So limit n approaches infinity here. Let's have another one here. So limit of n approaches infinity, this is going to be 5 to the power of n times 3n plus n to the power 4 divided by 3n times 5 to the power of n minus 2n. So we're going to split the dominant behavior. We have limit of n approaches infinity times 3 to the power of n plus n over 4 divided by 3 to the power of n, 5 to the power of n, 5 to the power of n minus 2n. And we're going to get limit of n approaches infinity 1 plus n over 4. And we have, this is going to be divided by 3n. We have 1 over 1 minus 2 to the power of n all over 5n. So then we can see that as n goes to infinity, we're going to have this n over 4 over 3n. This is going to go to 0. And this part here is going to go to 0. So we're going to be left over with, this is right there. So this is going to become 1 times 1. And we know that's equal to 1. So because we have our limit is positive and also finite, and we also have the comparison geometric series converges. Comparison series converges. Therefore, we can say that our original series up here converges. So now we can see that we can do another example. Okay, so we have these series to infinity. N is equal to 1. We have negative 1 to the power of n. This is going to be alternating our signs. So we have n squared plus 1 over n to the power of 3 plus 4. So first what we're going to do is we're going to check the absolute convergence. Absolute convergence, which means we have the summation here, right? We have to infinity, n is equal to 1. Absolute value of negative 1 to the power of n. We have n squared plus 1 over n cubed plus 4. Absolute value, that's going to equal to the summation of infinity, n is equal to 1, n squared plus 1, all over n cubed plus 4. So if you have a large n, you're going to have that this right here, this is approximately going to be equal to n squared over approximately n cubed, because you're not going to really care about those constants anymore. So we're going to compare this series to the harmonic series, which is when you have the summation of to infinity, we have starting at n is equal to 1, 1 over n. So we know that this is going to diverge. Now we're going to use the limit comparison test. Limit comparison test. So if you have the limit of n approaching infinity for n squared plus 1 over n cubed plus 4 all over 1 over n, this is the same thing as you have n times n squared plus 1, right, divided by n cubed plus 4. And this is, also have to write the limit symbol over here. This is the same thing as limit of n approaches infinity for n cubed plus n all over n cubed plus 4. And this is going to be equal to 1. So we see that the absolute value series diverges. Now let's check our alternating convergence. So let's let a to the sub n is equal to n squared plus 1 all over n cubed plus 4. So first a to the sub n is going to be greater than 0. So we also know that limit of n approaches infinity, an, is going to be limit n approaches infinity, n squared plus 1, n cubed plus 4. So let's divide everything by n cubed here, divide by n cubed here. We are going to get, this is equal to limit of n approaches infinity for 1 over n plus 1 over n cubed divided by 1 plus 4 over n cubed. So our terms are going to decrease eventually. Terms decrease eventually because the function behaves like one over n, which is going to decrease for a large n. We have that here. This is going to go to 0. This is going to go to 0. This is going to go to 0. This is 0, 0. So then we just have 0 over 1, right? That's equal to 0. So therefore, we can say by the alternating series test, the original series converges. So since the absolute value series diverges, though, we have to say that the series converges conditionally. So let's do one more example where we are looking for the radius and the interval of convergence. Let's say we have the summation of to infinity n is equal to 1. We have n x minus 2 to the power of n, 4 to the power of n. So we're going to use the ratio test. And we're going to say that a sub n is equal to n x minus 2 to the power of n divided by 4 to the power of n. So if you have a n plus 1 is equal to n plus 1 times x minus 2 n plus 1 all over 4n plus 1, we can compute a of n plus 1 divided by h sub n. So that's equal to n plus 1, absolute value, times x minus 2 to the power of n plus 1, all divided by 4 to the power of n plus 1 times 4 to the power of n divided by n times x minus 2 to the power of n. So that's all an absolute value. So if you cancel stuff out, we can cancel out that right there. We have n plus 1 left over here. We have this divided by n. And we have x minus 2 left. And this is divided by 4. So this is the same thing as n plus 1 over n times the absolute value of x minus 2 divided by 4. So now we're going to take the limit. We're going to take limit as n approaches infinity for this right here. So as we go towards infinity, this is going to just be like x minus 2 over 4. So for convergence, the ratio test is going to require for x minus 2 over 4 to be less than 1. So x minus 2, absolute value, less than 4. We have negative 4 is less than x minus 2, less than 4. So if we divide, we have, or we add 2 to both sides, I mean. Plus 2, plus 2, plus 2. We have negative 2 here, and x, and we have less than 6. So therefore, our radius, which is equal to big R, is equal to 4. Now we're going to check our endpoints. So endpoint 1 is going to be x is equal to negative 2. So we're going to sub in x equals to negative 2. X minus 2 is equal to negative 4. So we have series n is equal to 1 and negative 4 to the power of n over 4 to the power of n, which is equal to series of n is equal to 1 and negative 1 to the power of n. So the terms don't approach 0. We have the limit of n approaches infinity and negative 1 to the power of n does not exist and does not equal to 0. So it diverges at that endpoint. Now let's try our other endpoint. So endpoint 2, we have x is equal to 6. So if we sub in x is equal to 6, we have x minus 2 is equal to 4. This is going to be the summation of n is equal to 1. We have n 4 to the power of n. We have this over 4 to the power of n. This is going to be the summation of to infinity, n is equal to 1. And this is going to be n. So this is going to diverge. This diverges because terms don't approach 0. Therefore, we're going to say that our interval of convergence is going to be from negative 2, 6.